Hello viewers and my dear students. Welcome to session 1 on harmonic analysis. I'll be showing you a demo on harmonic analysis of a cantilever beam using Ansys release 14. Before we start with this, I'll be giving you some of the basic concepts related to harmonic analysis. See here, harmonic analysis is any sustained cycle or repeated load will produce a sustained cyclic response in a structural system. You will understand now. Harmonic response analysis is a technique used to determine the steady state response of a linear structure to loads that vary sinusoidally or harmonically with time. The idea is to calculate the structure's response at several frequencies and obtain a graph of amplitude or displacements versus frequency. Peak responses are then identified on the graph and stresses reviewed at those peak frequencies. This is the basics of harmonic analysis. Okay, but I'll explain you with reference to this sketch. Okay, you see here. See here, for this cantilever beam, I've already determined the natural frequencies. It is all fixed for this particular area of cross section, for this length and all that, for this material, that is steel, whatever I had given E 200 GPa and density some 7,830 kilogram per meter cube and all that. The critical frequencies or eigen frequencies or natural frequencies are all fixed. We know that for this particular beam, what we have already done in modal analysis, I'm taking the same example now. I'm taking the same model. Okay, for this beam, please understand, for this beam, we know already the first natural frequency is 8.16 Hertz. Okay, 8.16 Hertz for rotating shafts and all that. You can take it as 8.16 into 60. Okay, RPM. Okay, now you understand. First natural frequency is 8.16 Hertz. Second natural frequency was 51.15 Hertz. Third natural frequency was 143.25 Hertz. In that way, we had calculated theoretically. Okay, now the same has to be proved using harmonic analysis. We have a method here. You see here, you know very well for this, at least for two natural frequencies, we'll verify. First natural frequency is some 8.2. Second natural frequency is around 52. Okay. Now what you do is, as you know, the importance of these natural frequencies. That means, if this beam is subjected to, let us say, 1 Hertz per second, that is cyclic load, 1 Hertz per second, nothing will happen. 2 Hertz per second, nothing will happen. If it is subjected to load, that is sinusoidal load, 3 Hertz per second, nothing will happen. But the natural frequency is 8.2, no? In case if it is operated at 8 Hertz, that is, if you apply a forced frequency of 8 Hertz, that means if you apply the load here at the end, okay, if you apply the load at the end at the rate of 8 Hertz per second, 8 Hertz per second, then the resonance picks up. Can you understand? Immediately, you will have a maximum amplitude. That's what I was telling you. Maximum amplitude, creating a lot of stresses, and the structure is going to collapse. That is why I was telling you, you must avoid those frequencies. I'll repeat this. You see here, for this beam, the first natural frequency is 8.2 approximately, what we have already done in modal analysis, and the second natural frequency was 52 Hertz. The third and all that will not worry. At least for the first two, we'll do the harmonic analysis. Okay, that means first is 8.2 Hertz, the second is 52 Hertz, let us say. See here, now let us say you apply a load here. Apply a load of some 50 newtons or 100 newtons, one time in 1 second. 2 times in 1 second. That means 2 times in 1 second means it is 2 cycles per second. 2 cycles per second means 2 Hertz. Nothing will happen. If you one time in 1 second, if you see the amplitude will be minimum. 3 times per second, 3 hertz. Amplitude you see, okay, amplitude you see, the amplitude of vibration will be very minimum. 4 times in 1 second you apply the same 100 Newton, 4 times in 1 second at this end you apply. The amplitude will be minimum. But when you come to 7 hertz, amplitude goes on increasing little bit. Once you come to 8 hertz, if you apply the load at 8 times in 1 second, that is 8 hertz, that forced frequency matches with the natural frequency and you will have a peak developed. Okay, peak developed at 8.8, around 8, 8.2 in that way. Okay, then let us say you apply 10 hertz. Again, amplitude will be minimum. 15, 20 hertz, 20 times this load you apply per second. Okay, nothing will happen. 30, 40, 50 and all that, nothing will happen. Once you come to 52, which is another natural frequency, again you will get a peak amplitude will be maximum. That means again at 52, another peak will result. Another peak will result in maximum amplitude and resulting in maximum stresses. And this is what I was telling you. These are all dangerous frequencies. That means for this particular beam, for the harmonic analysis, at least I'll consider the first two natural frequencies. 8.2 is dangerous and 52 is dangerous, and you should not operate at 8.2 and 52. That is the logic behind this. That means these critical frequencies you must avoid. And if you operate at any other frequency, nothing happens to the beam. That is why finally in this harmonic analysis we draw a graph. On y-axis it will be the amplitude of vibration. On x-axis it will be the frequency. Let us say 0 to 100 hertz. Now 0, 1, 2, 3, nothing. Amplitude of vibration on y-axis will be minimum. Once you come to 8.2, first natural frequency, it picks up. The amplitude of vibration will be very much more. It is dangerous. Then again 9, 10 and all that, it will be again minimum and all that. Again once you come to 52, again it picks up. Then after 52 again dangerous. After that 52, 50, 60, 70, 80, 90 and all that, again it will be normal. Amplitude of vibration is normal. That means to say, when you are by doing harmonic analysis, you will clearly know where exactly are the peaks. The peaks are corresponding to natural frequencies, what you determined already. In one way, this harmonic analysis test will serve as a verification for whatever you have done in modal analysis. Modal analysis, you have got the first natural frequency as 8.2, second natural frequency as 52 and so on. And what we do here is, we draw a graph of amplitude versus frequency, and you clearly see amplitude will be minimum, and at 8.2 you will have a peak, and again at 52 you will have a peak, showing that they are all dangerous frequencies. That means amplitude of vibration increasing massively. As a result, it gives rise to massive stresses and collapsing of the structure and all that. Okay, now you see here, this is the problem. Now same things here. For the beam shown, perform harmonic response test by applying a cyclic load at the end of the beam. The frequency of the load will be varied from 1 to hertz, 100 hertz only. If you see here, the frequency of the load, if the load may be 100 newtons, okay, it will be varied from 100 hertz means, 1 to 100 means, I'll apply 1 hertz, 2 hertz, 3 hertz, 4 hertz, 5 hertz, 6 hertz, 7 hertz, up to 100 hertz. That means if it is 1 to hertz, 1 to 100 means you can have only two peaks only, because at one we know already in modal analysis the first peak is at 8.2, and 8.2 is the first natural frequency. At 8.2 you should have one peak, and 52 also you should have another peak. And since I have given 1 to 100 only, you can see only two peaks. If I given 1 to 200, that is 143 is another natural frequency, third natural frequency. You would have seen the third peak also. Okay, but as per this problem, even in V2 everywhere, they'll ask you to identify the two peaks and all that. 1 to 100 hertz you give. Determine the following. Draw a graph of amplitude versus frequency, and hence determine the first two natural frequencies of the beam. And if you find out the two natural frequencies at the point of peaks, where you have the peaks, they are the points of natural frequency. That should be verified with the modal analysis. and draw also the graph of amplitude versus frequency on a logarithmic scale. Same thing on a logarithmic scale. Okay, this is the problem given. Okay, now you see here. Now you see this is the thing, cyclic load I am applying. See here 100 newtons. Okay, 100 newtons I will be applying. At the end, it can be anything. Okay, cyclic load. But only thing is 100 newtons I will apply 1 hertz, 2 hertz, 3 hertz, 4 hertz, 5 hertz, up to 100 hertz I will apply. And I will draw a graph of amplitude versus frequency. Amplitude on y-axis, and on x-axis you will have a frequency 1 to 100 hertz, and you will see a two peaks, one at first natural frequency, and that is at 8.2. Another peak you will find at 52 hertz, what we have already done in that is modal analysis, as I have shown here. See here, modal analysis answers are this: 8.3, 52, 145, 285. These are all the natural frequencies. That means since I'm varying the load only between 1 to 100, 1 to 100 only 8.3 is there, 52 is there. That's why you'll find only two peaks. Okay, this is the basics. Please understand this. I'm repeating. Okay, please understand. This is the load what will apply sinusoidally. Okay, that means this load will apply 1 hertz per second, that is 1 cycle per second, 2 cycle per second, 3 cycles per second. That means 1 time in 1 second, 2 times in 1 second, 3 times in 1 second, 4 times in 1 second. In that way, yeah, we continuously operate this one. That means the cyclic load, no, 100 newtons will be applied 1 time in 1 second, that is 1 hertz. 2 times in 1 second, 2 hertz. 3 times in 1 second, 3 hertz. In that way, up to 100 hertz we will apply, and we will draw a graph of amplitude versus frequency. Once you draw a graph of amplitude versus frequency, okay, amplitude will be minimum throughout, except at the first natural frequency 8.3 and the second natural frequency of 52. These are all the things what you see, and you see here, I'll show you, this is what you are expected to get in the exam also. You see, amplitude versus frequency is the graph. This is what you are expected to do in the exam. Okay, this you draw. See here, at 0 to 100 I have applied. Okay, that cyclic load. At 8.2 approximately you have a peak, and again you see here the amplitude will be minimum. Anywhere you see here 22, 40, 45 and all that, it is minimum. Again at 52, okay, another peak is appearing. Okay, 52, another peak is appearing, and after 52 it is the amplitude of vibration will be minimum. These are all the safe frequencies. Unsafe frequencies are this. Unsafe frequency is this. That means 8.2 is unsafe frequency, 52 is unsafe frequency. Then next unsafe frequency is 143. Up to 143.25, you don't have to worry. The amplitude of vibration will be minimum only. This is the basics what you are supposed to know. Okay. Now once you know the basics, we will go for the answers. As usual, you do file, clear, start new. I'm doing from the base. Okay. Okay. That is from the starting only. This you do. Then say fit. Then as usual, file, change job name. You give it as that harmonic. You create a new log file. Okay, this you do, and also you change the job title also. Okay, file, change job title and all that, and we'll start with doing this problem. This is the end of session 1 on harmonic analysis. I'll give you a clear demo in session 2. Okay, about the harmonic analysis and how to get the peaks and all that. Okay, everything you'll know in the session 2 of harmonic analysis demo. Thank you very much for watching. Thanks friends. Thank you.